This is the important issue. And and safety also very important, right? Safety is also important. And the important thing is this is with no human intervention, means that it is no human intervention, right? But but to achieve these things without human, the car should be, it has to drive autonomously. It should reach the destination safely, and at the same time, means if it sense the environment properly, then only it can reach the destination safely, right? So actually, there are 5 levels of autonomous driving, means levels are there. The first one, you can see, actually I'm unable to see this. Okay. So level 0, in level 0, there will be no automation at all. Means completely the driver is responsible for controlling the vehicle. Means whatever the current day system is level 0. Right? There is no intelligence applied to, these vehicles. But coming to level 2, the driver will be there in the vehicle, but he will not, you know, use the steering, hands off. He'll simply sit idle, right? So driver will be there, but the system itself will use the steering. And the thing is that whenever in case of some emergency, okay, so the driver can intervene, means he may take the control of the, he or she may take, the driver may take the control of the autonomous vehicle, and he may use some braking system or acceleration, or sometimes he can take the steering also, means in emergency situation. But simply the driver will be there in the system, means vehicle, right? Now coming to level 3, the difference is that in level 2 there is hands off, but in level 3 eyes off. He can also, he can close his eyes, and he can simply relax in the vehicle. The driver will be there, but he will be in the relaxed mode. But again, here we'll use some emergency alarm kind of things. So if in case of any emergency, again, within no time limit, like in real time, within fraction of seconds after the warning, he has to take the control, right? He has to take the control for some emergency purposes, suppose accident or something, if there is a chance of accident. So in that situation, so then alarm will rings, then he has to take the control. Now in level 4, you can see level 4 and level 5. So in level 4, similar to level 3, but his mind is also off. He may be in the completely sleeping state, right? And he may be in the vehicle or he may not be in the vehicle, right? But again, based on requirement, some emergency situation, for safety reasons, so he will be there. But in level 5, this is complete automation, no human intervention at all required. But the current day systems as of now are at level 3. The research has happened up to level 3. Okay, the complete autonomous systems, like for long distances, okay, shorter distances, nowadays trials are going on, but level 3, up to the current research is at level 3. Okay, still there is a scope to, for level 4 and level 5 also. Now, coming to the challenges for the driverless cars, mainly in Indian scenarios. So, driverless So driverless cars require several systems actually to function properly and provide input, such as systems to, because the challenge is mainly in Indian environment, the road conditions are very poor, right? Means potholes will be there, maintenance will be very less, right? And the first one is this thing. And coming to the second one, it should know about the surroundings, whether any other vehicles on the road, or whether any other obstacles like that. It should also know the other means the other conditions, other means obstacles are like this on the road, because to avoid accidents and all these things, right? And to apply brake or to use acceleration, So based on that only, we can generally, as a driver, will use those accelerator, brake, and all these things. Okay, this is the first one. And second one, coming to the third one, as a human, we know the traffic rules, right? The traffic rules like yellow light means green light, we have to stop, red light, sorry, green light, we have to move, red light, we have to stop, and that, the timer will be there on the traffic light. Okay. So these traffic rules also means we need to, means for an autonomous vehicle, it has to learn these kind of things also. And anyway, this we already covered, like any abstraction, like other vehicles, animals, or humans, or these anyway covered. So in our research, actually, we tried to develop these support systems for the autonomous vehicles, like based on the road conditions. So how we can the autonomous vehicle has to detect the road condition, and how means we can address this, right? And in other one. Is there any chance of other vehicle to vehicle accident detection, like is accident detection? And one more support system we developed is traffic pole detection, and it's that light color, as well as the counter, how much time it has to wait, or the counter value. Green light means we have to move within that time. Suppose red light, there is a counter like 20 seconds, so we have to wait for 20 seconds. So like that, we developed a system for this. And so to know about obstructions like animals, humans, based on that, any chance of accident. So these things we developed. And one more actually here not covered, like the traffic sign detection also. We have one work, but this is a different work we did. I'll show you at the end the different works, whatever we focused. And these are all published works only. Yeah, for these are the frameworks actually we developed. As of now, I want to explore these frameworks. The first one is lane detection, because for an autonomous vehicle, as a driver, generally there will be on road, there will be two lanes. Okay. Suppose if you take the ring road, there may be multiple lanes. But while driving, we need to choose one of the lane. So we must be stick to that lane, right? So for this driverless car also, first it has to detect and which lane it is going, right? So for that, we developed a method like lane detection method. Later on, fixed this traffic timer and traffic pole, the counter detection. Is there any vehicle to animal accident detection, vehicular accident detection, and pothole detection? Right. The first one actually here in lane detection, we have applied simply some image processing techniques, because this is a simple process, because deep learning require a lot of computational things. But for this thing, simple image processing, like methods like image enhancement, like that filters we applied for to get this lane information. Yeah, you can see here the camera will capture the camera in front of the car, or that autonomous vehicle will capture this input frame. Assume this is the input frame captured. Now it has to identify different lanes. Suppose, let's say our vehicle is moving in this direction, right? So it has to identify this lane, correct? Okay, so for that, first what we'll do, we'll enhance the image. The first step in any image processing application, whatever the captured image has to be enhanced. And if any, because the captured image may be of not that much clear, right? Because of, environmental conditions like lighting conditions, suppose, or the camera resolution. So these different factors will affect the captured image quality. Okay, so that's why in any image processing application, the first step is image means improving the clarity of the image. So for that, we'll apply a few enhancement technique like histogram equalization, or some contrast enhancement techniques, some noise removal techniques like filters, median filters, mean filters, Laplacian. Some filters will apply so that the image will be enhanced. So here simply actually because in autonomous vehicle, because that is critical application. So that's why generally the camera quality will be good. Otherwise, what will happen if there is a small error, it will cost a life of a human, or right. So that's why generally we'll take uh, the camera, whatever the camera used will be high resolution only. But still, okay, we have to use some here we used simply the contrast enhancement using blurring the image. Okay, the next step is, after enhancement, just applied a canny edge detection method. This will be available in Python using, an open, some a built-in function is available, canny, right? So, and this canny edge detection is a, most effective edge detection method in image processing, right? So, how the canny edge detection will work, it will the edge detector, whatever the edge detectors, they will work based on the intensity variations. Suppose if you observe, this is the sky and this is some greenery pot trees. And coming to down, there is a red car, and coming to down, there is a tar that is black color. And here there you can observe some white lane, and here these are white lanes. Again, you can see some gray color, then dark gray, then again greenery. So you can observe the intensity variations in the picture. So the edge detectors will work like if there is a sudden intensity change, so those sudden intensity changes will be marked like this. Right? So these are the edge detector output. So sudden intensity changes will be converted into edges. You can clearly see this picture, image C, right? Now, the fourth step is after getting the edges of the image, right? Now we can see in the on the captured image of the image, you can see the upper part. Mostly it is sky. So we are interested in the lower part of the image. That means the lower part means here, right? So what we will do, we'll mask out. Mask out means we'll completely make it as black. Means we'll convolve with some filter like zeros, so that in the upper part, so that the complete part becomes black. This is not, we are not interested in this particular part, because the lanes will be in the lower part of the image, right? Now, we skipped out this thing, right? So we are interested this one. So the output of the masking out the upper half of the image, since the lanes are present only in the lower half of the image. So this is the output of the masking operation, the image D, right? Now the image D, if you observe, this lane started here, and there is a gap in the pixels, white pixels. Means the white, there is a gaps in the, actually, if you observe, uh, there are few, in the between the white pixels, these the black pixels are there. These are called the gaps. Actually, the complete line will be there, but unable to capture here. So using Huff transformation, the Huff transformation transform the pixel dots observed as edges. That means into an understandable lines. You can observe here. So this one is completely in the figure E. This is completely make just made straight. The gaps are filled. The black gaps are filled, right? Then, then this particular Huff transformed output is overlapped with the uh, original image, the main first image, the original image. Means this one will be overlapped like these. Means here you can observe. Here you can observe like there are the lane is the white pixels are not continuous. So now if we overlap this thing into that, you can observe this is the output of that. Then finally, finally we'll take the dominated line, like in this particular image. Finally, you can observe only these two, because these dominated lines are remained. So this will considered and as our particular lane, right? So the smoothing will apply some smoothing, and so that we'll get a smooth line, right? So that gives us the final markings, right? So this is a simple method using image processing techniques only. We are able to detect these lanes. Now these lanes will be, while in the next modules also we'll use this method to, suppose is there is a suppose some animal is there here while our vehicle is moving on. So to means predict whether there is a chance of accident, means whether there is a chance of hitting this animal by our vehicle or not. So those predictions, for those predictions also we need to require these lanes. So that's why as an initial step, uh, we started with this lane detection, right? Now coming to fixed traffic light signal and its counter detection. Okay, this is actually two part. First, we need to identify the traffic light. Then over the traffic light, based on that, the color information, and based on that, the counter value also. So it is developed in two stages. So this is the framework we used. This framework actually based on mask RCNN. Okay, so this framework is based on mask RCNN. So mask RCNN is a object detection model. Object detection model. Okay, so basically there are many object detection models, but I'll explain. I will discuss at the end why we use mask RCNN. Right. So there are RCNN family like basic RCNN, fast RCNN, faster RCNN, then mask RCNN, and nowadays people are using YOLO also. But the main important thing why we used mask RCNN, there is a special advantage for autonomous vehicles. So that's why we used instead of this YOLO, mask RCNN, sorry, faster RCNN, fast RCNN, RCNN. So anyway, basically these all will use the backbone of these all object detection models is CNN only for feature extraction and classification, right? So, right. Anyway, the mask RCNN is built over this faster RCNN. The limitations, if you want, I'll explain with 1 or 2 minutes. Actually, in the literature, earlier people use it for object detection also. Traditional methods. First, they'll extract features like, shift-based features, surf-based features, HOG features, like that. But later, the paradigm, like deep learning, people are using. So in deep learning also, actually, there are three types nowadays people are using, like RPN-based, that means region proposal network based, RPN based, and next one is single stage networks and multi-stage networks also there. So single stage neural network, that is like our YOLO, SSD, these things. And nowadays people are using transformer based methods also for object detection, right? Anyway, we are actually concentrated on RPN based because of few advantages which we require for autonomous vehicles, right? So, actually coming to RCNN, the main thing is that YOLO, these are all single stage networks, like they will directly do the prediction. Means like suppose if we apply an image to that detection model, the final outcome itself it will give, like whether if a cat, suppose let us in an image a cat is there, dog is there, a human is there, some trees are there. Simply it will give this is cat, this is dog, this is human, this is car, like that it will give. Okay, but here in our case we require some masks, actually these masks and uh, uh, these region proposal networks will give us also, anyway, YOLO also give the coordinates of that particular object in that image. Coordinate means where exactly that image is, where exactly that object is. Sorry. right? So that's why the RPN, these are two-stage networks, whereas this YOLO and all these things are single-stage networks, right? In two-stage networks, so first they will extract the regions, right? Region proposals, like where exactly the object is there. Then it will give the whether it is a car, whether it is a lorry or bus or a dog or a cat, like that. Okay, it will give the region as well as that uh, classifier, that output, right? So now coming to RCNN, anyway, RCNN. In 2014, I think his name is Girshik. In 2014, he developed this RCNN model. So, but this in RCNN, this is R stands for region, right? So these regions were basically to get these regions. So they use in RCNN they used some external algorithms like this image processing methods, and they try to get that regions. Okay, then over those regions they applied CNN for feature extraction, and finally the classification will be done using SVM in RCNN. Okay, first regions are extracted by using an external algorithm, right? Then over these regions, CNN will be applied to extract the features. And for classification, SVM is used to predict which object is that, right? So that is RCNN. But later stage, this fast RCNN also introduced by the same, Rishik in 2015. So where actually in the RCNN, what happened? Over the regions, over the individual regions, the CNN was applied, right? Means CNN was applied multiple times. Suppose in that image, some dog is there, cat is there. So after identifying those regions, CNN will be individually applied over the regions. But coming to fast RCNN, so the complete image first means first using CNN will extract the features. Okay, so CNN will be applied in fast RCNN. First CNN will be applied, followed by RPN over the extracted features. Uh, over the extracted features using some ROI pooling layer. Here also we'll use it, ROI align. See, in RCN mask RCN also we'll use it. ROI align method will get the regions. Now over this using this these region features only considered for object classification and prediction, and object classification and the box prediction, right? So the difference is that we are reducing the complexity. Instead of applying CNN multiple times, here with fast RCNN, this becomes faster because CNN applied over the entire image. Then the regions will be calculated. Now coming to faster RCNN. So here, first, sorry, okay. Okay, so before, before this ROI pooling, yeah, the CNN actually in fast RCNN, what happened? Over CNN, we are applying this ROI align, right? ROI align and getting that, the features for object this detection, right? But in faster RCNN, yeah, instead of a separate algorithm, the CNN first will apply the CNN, then uh, the so few RPN layers will be applied over the extracted features of the CNN. Then using a new loss function, actually that some optimization will be applied here. Optimization will be applied here, which helps to improve the accuracy. Actually, the means there is a little change with fast RCNN and faster RCNN. So the simply some optimization method is used for object classification and box regression. Right now, The mask RCNN, actually mask RCNN is, you can observe here, actually I will show you the mask RCNN first, the architecture of the mask RCNN. See, again, here, this is the input we'll apply. This is the input, right? This image. This is the image applied to the CNN for feature extraction, right? Then this CNN features will be given to the region proposal network, RPN, right? Then an ROI align layer will be applied. So whatever the regions extracted may be of different shapes. So to make them of a unique shape, so we'll apply this ROI align layer. So which will convert these, these different shapes. This is different shape. This is different shape into a fixed size feature map. You can see, right? Then this part is same, like faster RCNN. Then this will be applied to a classifier that is applied to fully connected layer. Then here the class it is given to the classifier for classification and box regression. But only change with the faster RCNN and mask RCNN is that this mask branch. So it will generate a mask, okay, a binary mask, either 0 or 1, like whether that object, over that object, exact mask will be given. Actually, this we will use in our uh, accident prediction methods, like, vehicle to vehicle or vehicle to animal accident prediction, right? So that is the reason, because of this mask will help us, the mask will help us to predict whether there is an accident happened, or there is a chance of accident there is a chance of colliding with some animals, like that. So that's why this mask cars, and this will give us some extra, input while prediction. So that's why instead of these YOLO, these other object detection models, we preferred this mask RCNN, right? Now you can observe here. So mask RCNN was developed on top of a faster RCNN, which we discussed. This particular portion is faster RCNN, right? And the difference is this mask RCNN, right? Now the mask RCNN consists of two stages, that is stage 1 and stage 2. So this is this is stage 1, which consists of two backbone CNNs. This is two backbone CNNs, right? This is one CNN and this is RPN, right? So two networks, a backbone network that is that may be a ResNet. This CNN may be a ResNet, a VGG, or deep CNN, but people generally will use ResNet 101 architecture at this particular CNN place. ResNet 151. Sorry, ResNet 101 architecture they use, right? Then the first stage, this CNN followed by a region proposal network, that is RPN. So RPN is used to give region proposals and are run once per image, once per every image, because the input image will be given to CNN. The feature maps will be directly given to the RPN for region predictions, right? Then this is stage 1. In stage 2, you can see it will be given to ROI align layer. This is the ROI align layer to convert these variable shape feature maps to fixed size feature maps. So size of these proposed regions is equalized using ROLN. Then that will be given to the fixed size feature maps will be given to the, here this is fully connected layer, and this side it is given to the mask branch. Okay, so this side you can see the predict object classes and bounding boxes for all proposed regions. The proposed regions, the bounding box as well as the class will predict. And the masks are generated for each segmented object in the mask branch here. Okay, so this will use in our other frameworks. Okay, now we'll come back to our traffic. Yeah, I'll remove all this. Yeah, any questions, please?
Good afternoon, sir. This is
Yeah, yeah.
Reddy from Department of AI, Anurag University. So you think that there will be external algorithms that will be used. So may I know what will be the other external algorithms that will be used?
Where in region extraction, sir?
Yes, sir.
Uh, like, the segmentation methods, like, suppose generally to extract the regions in image processing using external algorithms like segmentation. Suppose if we apply some thresholding method or segmentation methods, OS2 thresholding method, right? So that we can get the exact object shape where exactly an object may be there. Okay, that type of external algorithms they have used actually.
Okay, sir. Thank you.
Yeah.
Participants, have any questions to be asked to the speaker, sir?
Sir, your voice is very low, sir.
Ask questions in the chat window, participants, so that sir will see and reply to your queries. Okay.
Yeah.
Thank you, sir.
Okay, thank you. Right. Now, anyway, this is the input image captured by the camera, right? For traffic light signal and counter detection. So this is the title, traffic light signal and counter detection. So let's say here, this is the input image. Now this input image will be given to the, in the mask RCNN, the first level is CNN, ResNet 101 architecture, right? So will be given to the CNN for feature extraction. Now these features will be given to the RPN, right? So to predict the regions, so instead of external algorithm, here we are using RPN, right? Now it will generate a feature map of variable shapes. Then using ROLN layer, we'll convert it into fixed size, feature maps. Then we can able to get the classifier, like whether that is a traffic light or not. So the output of this one is the traffic light. Means we are interested in traffic light, right here. So if that is traffic light, with what confidence, and the box means bounding box, right? And a mask it will also give. But here in our case for traffic light, this mask is will ignore this mask. But we are interested here only this box and this thing, right? Now, so the traffic light, whatever here extracted, these are the crop traffic light. Then uh, then the next step is we need to identify, right, that light, right? Then light and further the counter value you can see here, right? So you can see here this is a combined the complete output. So first we'll apply this input image to the mask RCNN. So the mask RCNN output is it will give the traffic light. This thing is a traffic light, crop traffic light you can see, right? Then from this crop traffic light, then we need to identify, okay, here actually, here in our case, so, okay, the color, that information we haven't considered, but only main thing is the counter value. You can see here after traffic light cropping, just to get this counter value, right? So we need to extract this information, right? This information. Then we have to classify, right? Whether that is 4 4 or 5 4 or 5 3 or 5 2 or whatever, right? So because numbers are generally 0 to 9, only 10 digits will be there, right? So to classify what exactly this number, we used a retina net, a lightweight model. Retina means it will be, a, that is a smaller, a lightweight model with less complexity, right? Because here the task of this classifier is to, distinguish between only 0 to 9, whether 0 or 1 or only 10 digits are there. So the classification is we require very less computational, right? Computational power, right? So that's why here use RetinaNet to detect the lights, right? So this is a final output. But to get this one, you can see after extracting the traffic lights, then some more methods we applied, like some masking operation to exactly get the object like this counter value, because wherever we are focused on only that counter value after detecting the traffic light, right? So that's why we used in masking operation. So we'll discuss that one step by step, right? Okay. Now, anyway, signal detection that is over using mask RCN we did. Then this is the crop traffic light, right? Then we will do some thresholding operation because we are focused only on this thing, right? The remaining content is useless for us, right? So that is not required. Only we are interested in this thing. So to get only that thing, generally we'll use masking. In the lane detection also, we are interested in the lower part of the image. So that's why the upper part we masked out, right? So the masking operation generally we can do using, thresholding or suppose because in between the lane detection the upper complete part we masked out, there we multiplied it with some zero so that everything will become zero means in image processing that is a black pixel, right? So that's why. But here in between, so this 44 you can see other pixels also there, right? So we need to be very careful while masking, while doing this, while getting that uh, digits, right? So that's why here fast CTV is converted into, RGB image is converted to HSV, right? Then we will perform some thresholding. Yeah, step by step we'll see. The first one, yeah. So actually the thresholding, what it will do, suppose let's say, mm, thresholding will convert an image into binary. Binary means either 0 pixels or 1 pixels will be there. One stands for white, means one means this is a grayscale value is 255 actually, and pixel 0 stands for black. Now you can observe. Here within this image, this pixels that constitute this 44 and this arrow. Pixels that constitute pixels that constitute this 44 and arrow are of different grayscale, and remaining image, these pixels are of different, right? You can observe. Okay, so based on the pixel intensity at this digits 44 and this arrow, because they are same, the pixels above, suppose let's say 44 pixel is having intensity some 200. Now 200, if I fix some threshold like suppose some 199, or let us assume less than 200, threshold less than 200 will make them black. Okay, so pixels with intensity less than 200 will become black, and above 200 intensity will become white. Above or equal to 200 will become white. Now easily we can do it, right? So the pixels, because the 44 and the digits will have intensity 200, so they become white, and remaining pixels, because their intensity is lower than that, so they become black. Now you can see this is the black and white image, which you can see here, right? Now, now we will apply the masking operation by doing some AND operation. Suppose now this binary image, this is called binary because 0 and 1 pixels will be there, right? So this will be performed some masking like AND operation between the original image, whatever the mask RCN output. Now, if we perform AND operation between these pixels, the corresponding pixel positions, see at 44 and this arrow, we have pixel intensity 1. So 1 multiplied with these intensities. You can see these intensities are now very clear. We are reproduced these intensities by doing the masking operation. The remaining thing, because this remaining thing completely becomes black because we are multiplying with 0 intensities. All these are zeros, right? So that's why we are able to get the original, the cropped and only extracted digit information. Now, this information will be given to retina-netted model for classification. What exactly these digits are, right? So it is giving us 44, right? So 44 seconds our vehicle has to be, as a human we know that is 44, but for machine we need to feed. So it has to wait for 44 seconds in that junction, traffic at the traffic light position, right? And wait are based on, again we need to actually, we can do this analysis also, color analysis like green, red and yellow. Okay, so that actually we haven't considered, but only thing main aim is actually this is a second work. Never it, I think only one paper was there earlier to us for this counter detection, traffic pole detection. Many works are there, but this is the second work actually we did with with the deep learning. Earlier method also that they used simple some image processing algorithm for this counter detection, traffic timer detection, right? So this is our final output. You can see here the rated value is 44 and we displayed the result over the same image. Right. Now, this is a mask carcinogen anyway we discussed. Right. Now, the second module is vehicle to animal accident detection. See, here again we used, because, any object detection model we can use, but only thing mask RCN, the masks are helpful for us. And one more important thing, for fixed traffic light, this traffic light detection, mask RCN is not required. Simple faster RCN is sufficient, but only our aim is to develop a combined model for all these frameworks. So uniformly, we applied, mask RCN. Right. So for all the frameworks, we used mask RCN only, but this one is not required actually. Right. Now, again, vehicle to animal accident detection, right? First, like traffic light, we need to detect the animal, whether there is an animal or not. So animal is again an object. So for animal detection, again, we used same mask RCN. Now the mask RCN output is the animal, right? The classifier output is animal, right? Right. Generally, here we use like actually in Indian scenarios, basically we included cows and dogs here because these are basic animals which we can observe in the Indian environment, right? But it can't do anything, right? Then, after detecting the animal, whether that animal is approaching, because our vehicle is going on a particular lane, right? Using that lane detection, we can able to identify lane, and now we are able to predict, that animal. Now, based that animal is whether, is there any chance of hitting our vehicle or not? So that we need to identify, right? So that's why here this lane analysis and all those things again. Here, you can see lane is used to determine if an animal is on the path of the vehicle or not of our autonomous vehicle, right? So if an animal is not within the lane, we use it as the backbone for predictive feedback mechanism of approaching animals, right? So if it is not in our lane, right? But is there any chance that animal is approaching our lane and is there any chance of collide? That will give it to the input to the predictive mechanism, right? Now, this animal direction and vicinity tracking, actually here we used a centroid tracking algorithm for this, that animal tracking. Yeah, it is there. Centroid tracking. Animals are tracked using centroid tracking algorithm. If an animal is outside the lane but moving towards our lane, we can alert our autonomous vehicle beforehand using the predictive feedback. Okay, based on that following. The animal is outside the detected lane and is moving in the direction towards it, right? And the animal is in the vicinity. In the vicinity means it is very closer and there is a chance of hitting the our vehicle, right? So the centroid tracking algorithm is basically, between successive frames. Suppose, let's say, because our camera is capturing the video, so generally video consists of some consecutive frames, right? So suppose, let's say our vehicle is moving like this and the lane is this one. The camera is capturing, this means capturing, suppose, the environment like this, right? Now, first, in the first frame, because we are capturing video, right? Initially, the animal is here. In the next frame, maybe here. Next frame, maybe here. Means, if you observe in the first frame, if you take the centroid of this animal, because we are able to predict these bounding boxes, right? Using mask or CNN, we can able to predict this its centroid, the center point. But in the next frame, you can see the centroid will comes to this particular place. If you observe the distance, the Euclidean distance or something, so this between these 2 points and how closer are these to our vehicle. If that distance is minimizing, means the vehicle is animal is approaching our this thing, right? And with how much speed it is approaching, we can predict using this centroid tracking algorithm, right? You can see this centroid tracking algorithm somewhere here also, right? So in the first image, the animal centroid is this. The second image, the animal centroid is this. Now, based on these distances and these bounding boxes, we can easily say Euclidean distance between the centroids to detect vehicles over consecutive frames. Like in our case, this is animals, right? So the same algorithm we applied here, right? Right. Now, an animal is in the vicinity of the autonomous vehicle if its centroids lies between the horizontal midpoints of the lane. Now, let's say based on that, we can say whether it is approaching or not, right? So based on that, we can intimate the alert system, right? Or suppose, let's say now these are the lanes we detected. If you draw a horizontal line to this and if you draw a perpendicular line to the centroid of our detected animal, if it is perpendicular to that, we can say that the way the animal is within the vicinity of the our vehicle, and there is a chance of hitting. Therefore, if an animal is moving towards the lane and in its vicinity, we can predict that an animal is a hazard for the autonomous vehicle even before it actually enters the lane. Even it is not enter the lane, but using this mechanism, we can detect if it is on the vicinity. Or based on the central tracking algorithm, what we said, whether it is approaching or not, right? So based on that, we can do this. So now combination of these two stages, if the road is unobstructed, means it is not in the vicinity. If an animal is present within the lanes or near the lanes, you can give a stop signal, right? So based on that, we'll work. See, this is stop, right? Now, the next one is vehicular accident detection. Again, this is the previous case. What happened? That is there any chance of obstacles like human, other animal, or other vehicles, or like that? But now this is a special scenario. Like while our vehicle is going on, let's say some accident was happened somewhere here between two. Generally, accident means what? Between two, basically between two vehicles, right? So if we are able to track those two vehicles and their status, whether they are moving or not, and here the masks will be come into picture because we are able to get the masks, right, using mask RCN. So the masks, we can use this IOU mechanism, intersection over union. If we combine these two masks, and what is the intersection rate? If it is greater than 0.5, some threshold, means between those two masks, there is a chance of, there is a 0.5, means half of the masks are overlapped, then we can say that. And one more condition, they are in still state, right? They are not moving. So we need to predict the speed of the vehicles also. Based on the masks intersection, that is intersection over union, we'll use this parameter and their speed. Right? If the speed is, there is no speed and IOE is greater than 0.5, we can say that there is an accident happened. So for this autonomous vehicle, we can apply the brake. Okay, so like that this will work. So for that, these are the mechanisms again. So vehicle detection, vehicle tracking. For vehicle detection, as already told, we will use MASCAR CNN. Now tell me what is how we can track the vehicle. Vehicle tracking we can use again the centroid tracking algorithm. What we will use it for animal tracking. So centroid tracking algorithm using centroids of that bounding box. Then vehicle overlap we can do using these masks generated. The output of these masks are seen as one is mask, one is class, one is box. Right. So these masks here we are using. So that's why for this application we use a mask RC. Right. So means because our aim is to combine all these frameworks. So that's why in everywhere and ultimately we want an object detection model, but with mask RCN we have this added advantage. So that's why overall in all the frameworks we use this mask RCN. Right. Then is there any vehicle overlap using that? Now we need to do some lane detection, because whether these vehicle overlap is in our lane or not. Okay, then this vehicle trajectory and their speed detection, because there is a overlap, because on the same lane if two vehicles are going on, their mass, there is a overlap of the masks, but we need to consider the speed also. Right. So based on that speed, finally we are able to detect whether there is an accident happened or not. Right. So this is the mechanism. So for vehicle detection, what I told, we use MASCAR CNN. Right. This is a MASCAR CNN for vehicle detection. Then for vehicle tracking, we use a centroid tracking algorithm like animal tracking. Then vehicle overlap using these masks. In any vehicular accident, the two vehicles must collide. This means that in an instant, these two vehicles must be overlapping in a frame. This overlapping can be easily determined if the mass generated by the mask or CNN are overlapping by taking the intersection overview. Right. Then lane detection, whether that acts, because if these two masks generated for this particular car and this particular lorry, are, you can see there is a 50% overlap of the masks over union, right? But they are moving vehicles, right? So that is not an accident. But some other case, suppose the speed is 0, right? So that's why based on that. But again, one more important thing is whether these overlap is in within our lane or not. So that's why we will do this lane detection and section-wise analysis. Then vehicle speed, based on vehicle speed, we can say whether there is an accident happened or not using some score generated based on some function we'll use actually here. Some function actually forgot to include. Some equations are there, right? So based on that, we can apply some acceleration, because if the accident happened in the same lane, suppose you can see here. So we can apply acceleration, means brake over the, means we can apply brake to the vehicle, means the autonomous system has to, means slow down its speed, right? So stop or go, that will be decided by the accident detection mechanism, right? The last framework is pothole detection, right? So I'll again here also we used the same, the mask CNN. These are the few potholes, right? And whether they are in our this thing or not, our vicinity or not. So this is some flow chart, means implementation details. These are used mask CNN for training the pothole or background, right? So implementation details these are, right? Here only thing is the classification of whether pothole is there or not. This is a simple road or pothole is there. So that's why mask CNN is sufficient here. Right. These are the few experiments. Right. We used this GPU NVDA, our GPU only. Right. And implemented in TensorFlow using OpenCV. And a few measures like precision, recall, and average precision, and detection ratio and false alarm rate. Suppose in the case of accident, So how many are detected accident cases and total accident cases? Suppose let's say actually there are 100 accidents happened in our taken in the data set, but our system is able to identify only 90. So that is a detection ratio. And sometimes our method may falsely detect that there may be no accident, but it may detect it as accident. So that is false alarm, right? So based on that, the measures will be taken. And anyway, good results only we obtained. So whatever I said here was mask RCN, and these are the results. And the success rate of identifying that counter is 95.65 times, right? These are some curves. Now you can see the classification for these classes using RetinaNet 0 to 9, the precision recall values. And this is the framework, what I told, they used the color segmentation actually for what is that? Traffic light detection and counter detection. Okay, so there actually they used this traditional image processing models, and their results are good only. But anyway, our framework here, our intention is to combine all these things. But the precision recall values are little bit low, but even they are closer in to this result, right? This is for vehicle to animal accident detection. Anyway, the precision recall values are 86, 83. Accident, again, this is accident detection. You can see here, these are the few literature works. Here, for accident detection ratio, here in our case, it is improved because here 82%, 82%, here ours is 84. And false acceptance rate, here 0.08, 0.08, but ours is 0.02. Right? So false means the negative result should be low, right? So ours is very low, and here it is ours is high, right? So like that means somewhat here you can see this method performs 71 and others 80, but ours is 77.05, and false rate is very low, so that is good sign, right? Right. Right. These pothole detections also it is very good. Okay. See, you can observe here. There YOLO also, YOLO version 2, they have got 60%, but our framework is able to achieve 89 precision, right? So like that, in some cases, it is performed good, and still we are doing a few other, we are means using some other, latest object detection models like transformer based these things. We are trying to improve the results. Yeah. Any questions, please, before moving on to the biometrics? Because we have 15 minutes left. This is the experimental feature work, and better actually taken the data sets. No public data sets are available. You'll taken the data sets from YouTube only, right? And anyway, because this accuracy, less accuracy, maybe because of limited data set available, because for deep learning models, we need to have huge amount of data for training. Okay, that may be the reason, for getting some lesser results somewhere in traffic light or those things. So that's why more experimentation is required. And our ultimate goal is combining the system into a full application for easy implementation. Yeah. Any questions, please?
AI and our university.
Hello.
Hello, sir. How me?
Hello. Yeah, tell me, sir.
Sir, just how does an autonomous vehicle recognize
No. This voice is not proper, sir. Actually, you can type in the chat box also.
Yeah, I'll try it, sir.
Where is this chat box? I don't. Yeah, it is there, right?
Meanwhile, I request.
I first to start the speakers are.
Okay. Meanwhile, anyway, I will start with this biometric, security with deep learning. Actually, am I audible, sir? Am I audible, sir?
Yes, sir. You are audible, sir.
Yes. Okay. Okay. No issue. Just I'll discuss the problem and how we address it using deep learning. The problem in biometrics is that the main challenge, whatever I'm working, there are a lot of research areas in biometrics also. But the main important thing is actually biometrics we are using for uh, that mainly security, right? Security means suppose in place of nowadays in place of passwords we are using biometrics, right? Suppose it for our phone or laptop or wherever, suppose access control mechanisms, basically access control mechanisms we are using biometrics instead of passwords and pins, right, or tokens. But if we forgot some password, or if our password is compromised, let's say our Gmail password or our banking password is compromised, what we'll do generally, we'll click on forgot password and we'll get a new password, correct? But here the case is because alternative to passwords, we are using biometrics. But let us assume if we are using biometrics and if our biometrics is compromised, it means it is in the hand of some third party. That is a permanent loss, right? Permanent loss means because we have only 10. Suppose if you take 10, if you take fingers, we have 10 fingers, one face, two iris, one right? Right, one palm, right, like that. Suppose if one, let us assume we are using fingerprint system, and uh, if our fingerprint is compromised, then that is a permanent loss. Only we have to use, the other options are only 9, right? Let's say next time if we are using second fingerprint and that is also compromised. So overall only we have 10 choices, right? If you use fingerprint recognition. But in password based mechanisms, you can observe if a password is compromised, right? We can cancel the old one and we can get a new one, right? Right. So here also, why can't we have a fingerprint or biometric system such that if the old one is compromised, why can't we reissue a new one? Right. So that is actually the area is called cancelable biometrics. Cancelable biometrics. But before to that, so to protect the biometric characteristics, generally we need to use some template protection mechanisms. Because if it is in raw form in the database, like the image, suppose my finger is there in the database, anybody can access, because nowadays everything is based on biometrics, right? So anybody can access the database and can get my fingerprint, and they may duplicate it, like they can generate some synthetic fingerprint, right? And they can use it for malicious purpose. So that's why while storing in the databases, first thing is we need to protect them. We need to, means applying some cryptographic or some other mechanisms, we have to protect it. But one major limitation with cryptographic cryptography is that they are not suitable basically, because there are lot of computations will be involved. Lot of computations will be involved, right? In a RSA, or you can see DES algorithm, right? Lot of computations will be involved. So at the decryption side, so it requires a lot of time to, a lot of computing to decrypt it and to verify. But biometric system generally wants real-time verification, right? If it take a lot of time, then useless, right? So that's why we need to have lightweight cryptographic mechanisms to protect them, right? So that is one issue. The second issue is, even though if we protect them, sometimes they may apply, because cryptographic, the key is the important issue. If key is compromised, everything they can decrypt. Now again, that may be in the hand of third party. So that's why if that is compromised, we have to cancel it like our password, and we have to regenerate a new one. That is the other area, cancelable biometrics. So here actually we used for finger vein. So I'm not going into detail about what is finger vein because they are having some additional advantages. Right. So the mechanism here we applied is, you can see, this is a proposed model, simple CNN model we applied here. This is a finger vein image. Then it is converted into some, the image is encoded into a 1D vector. Like we have to write, because image is a two-dimensional, two-dimensional image is generally two-dimensional, right? So we have to convert it into 1D. Then we apply simple ECC encryption, elliptic curve cryptography mechanism, right? Then this one encrypted image, 1D vector, will be converted into two-dimensional. Then we apply some normalization, because, after applying encryption, generally the black and white image, grayscale image, the intensities will be in the range of 0 to 255, right? But if a value, let's say 200, is encrypted with some DES or some other encryption mechanism, the range, maybe it may be 10,000 or 1 lakh or whatever it may be, because that is the encoded value, right? The encoded value may be out of range, because we need to have for an image in the range of 0 to 255 to look like an image, grayscale image. So that's why again we'll do normalization between 0 to 255. Then we'll do some enhancement, image enhancement. Then this will be given for the model training, CNN model, right? So to get, that is right. These are the actually few results. This is the finger original image, finger vein. Their veins are under the finger, right? They can be captured using infrared light, right? So this is converted into grayscale. Then applying some encoding mechanism. You can see here, this is an image, 3x3 image. Let us assume it will be, we can use some mechanisms are there for encoding, local binary pattern, local ternary patterns or something. So converted into some decimal value here, you can see. Or we can also directly encoding, converting this image into two-dimensional image into one-dimensional. Here use two encoding methods, that is LVP and direct encoding. These are the few. This is after encryption using ECC. This is after normalization, because what I said, after encryption, the pixel intensities may be out of range. So to convert back to, this will converted back to 0 to 255 using normalization. Then after applying some image enhancing methods, like this is the original image, then average filter is applied, then median filter is applied, then Gaussian filter is applied to make the image more clearer. Then will be given to the, for training. This is the training model we taken, right? The few results actually, accuracy and loss you can see here, okay, with the direct encoding, and this is with LBP encoding, comparative study, right? So accuracy and error rate, right? Okay, anyway, this is one template protection mechanism, and one more, yes, I'll take 2 minutes only for that again. This is one more mechanism using machine learning we did. This is iris recognition and template protection using machine. Yeah. So here the first step for iris is segmentation, because iris is an of oval shape. So it should be converted into rectangle to process by, because to convert it into any, to give it into any model, it should be rectangular, right? So we can by using the segmentation step, segmentation and normalization, we'll convert into, you can see here, this is a, segmentation output. After normalization, we'll get a rectangular strip like this, right? Then it will be converted into some encoder mechanism we'll use. Then some features will be extracted using that. Then ML models will be applied. See, you can see this is the main important step in base 64 encoder is the important step for template protection here. See, this is a basic C4 encoder. Actually, we will convert these image pixels into text, image into text, converts the image to text. Because the image pixel values are generally between 0 to 255, we will convert it into text, as base 64 encoder, where we can represent A, B, C, D, E, capital alphabets, smaller alphabets, and 0 to 9, and some special characters. So these image pixels will convert it into text for encoding purpose, because if that template is in the hand of some third party also, it must be difficult for the third party to decode it. So that's why we convert, this image into text using actually this particular technology is called stylometric features. Actually, stylometric features. These are called stylometric features. After base 64 encoder, you can see after converting into text, based on from that text itself, we are able to get almost 25 features, I think. Here, this is 12 plus 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 features. You can see after converting the image into text, we are taking the features as the average sentence length in the text, the percentage of capital letters in relation to the number of lowercase letters. Suppose let's say the total characters are 200. In that, let's say capital letters are 70. So that is the percentage we'll take 70 by 200. So percentage of lowercase letters in relation to total number of characters. Percentage of punctuation signs, numerical characters, the average word length, the frequency of the most frequent stop word in a text, most frequent starting word, most frequent starting letter. So like that, some stylometric features will extract. So what is the main contribution here? Converting an image into text using base 64 encoder, then using these stylometric features, right? These features will give it to the classifier. Again, one more step is there, right? For the classifier ML model, right? For this thing. This is a key generation process. So these are the few results. This is a base image after random pixel selection, after key application. These are the few results. Okay, these are the two works actually with the deep learning and machine learning. We did with biometrics. Right? Before to this, actually, I also used simple image processing mechanisms for feature extraction and everything. Traditional methods are used. In my research also, I use the same thing. Recently, actually worked on these two problems with the machine learning and one is the deep learning. Yeah. So chat box. Yeah. Any questions actually? Hi, sir. If you are showing PPT slide. Oh, sorry. That screen is not
In
visible.
the
This screen.
lab.
Excuse me. Am I audible, sir?
మీరెందుకు-
Hello.
Yes, sir, audible, sir. Hello,
My
sir,
screen
you're
is not
audible, sir.
visible, sir. My screen is not visible.
We can see the future scope and opportunities to improve. We can see that screen.
Oh, sorry, sorry. Actually, I explained two more. Okay. Now it is visible, sir. Base 64
The same
encoder.
screen, sir.
Base 64 encoder.
No,
No,
we are at the same
no.
screen. No, no.
Sorry, sorry, sorry. Okay, 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 okay. Actually, I shown you this one first, just for. Sorry, sorry, sorry. Wasted time, 10 minutes. Actually, this is a model we applied for
Yeah.
a finger
Now
vein,
we can see the
actually.
proposed model.
Sorry.
Yeah.
This is the finger vein protection and finger vein recognition with template protection using deep learning, right?
Okay.
So finger means the biometric template
Sir,
protection.
can we wind it up in another? Uh,
Yeah, 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 yeah. Okay, okay, no issue,
yeah.
sir. Right, right. Yeah, you can wind up. But actually, I thought this PPT actually it is visible to you. I explained to one more PPT also along with this. Okay, sir. No problem. If any questions, please you can ask, and otherwise we can wind up. If no questions, we'll stop, sir. Actually, I have some other work. Yeah, if no questions, then we'll wind up, sir.